People always ask me why we're stuck with chemical rockets. Seriously, exploding a bunch of hydrogen or kerosene is the best that we can do? Good news, there are other exotic science fiction sounding propulsion systems out there which use electromagnetic fields to accelerate atoms, allowing their spacecraft to accelerate for months at a time. I'm talking about ion engines, of course, and several spacecraft have already used these exotic thrusters to perform some of the most amazing missions in the exploration of the solar system. I know, chemical rockets seem really primitive. Take tons of liquid or solid fuel, light it on fire with an oxidizer, and then use the speed of the explosive gases to give you a kick in the opposite direction. Thanks, Newton's third law. But chemical rockets do the trick. Those gases do give a rocket the kick it needs to get into space. Because they bring their own oxidizer with them, they work in the atmosphere and they work in the airlessness of space. The advantage of rockets is that they can deliver enormous amounts of energy in short periods of time, the kind of reaction you need to blast tons of cargo off Earth and into space. But they're incredibly inefficient. A 550 metric ton Falcon Heavy is carrying almost 400 tons of fuel and oxidizer. The first stage will only burn for 162 seconds, and the second stage will fire for 397 seconds. That gives you a total burn time of about 9.5 minutes. Want to make some maneuvers? Want to accelerate for days, weeks, or even months? Too bad, you are out of fuel. Of course, these shortcomings from chemical rockets have led scientists to search for other forms of propulsion, especially when you're out in space, and one of the most successful so far is the ion thruster. When you're working out the rocket equation, an important factor is the velocity that you're ejecting your propellant. The most efficient chemical rocket can throw hot gases out the back at 5 kilometers per second. Ion engines, on the other hand, can eject individual atoms 90 kilometers a second. This high velocity gives the spacecraft a much more efficient acceleration. The best chemical rockets see a fuel efficiency of about 35%, while ion engines see an efficiency of 90%. So how do ion thrusters work? It's actually pretty weird and totally sounds like science fiction. Instead of hot gases, ion thrusters eject ions, which are atoms or molecules which have an electrical charge because they've lost or gained an electron. In the case of an ion engine, they're emitting positively charged ions which have lost an electron. Once you've got ions, you can direct them with a magnetic field, accelerating them into space at tremendous speeds. So where do they get all the ions? The thrusters create them by generating a plasma inside the spacecraft, and they bombard neutral propellant atoms of some gas like xenon with electrons. These collisions release even more electrons from the propellant, turning them into positively charged ions. This plasma soup of electrons and positively charged ions has an overall neutral charge. The electrons are held in the chamber, leading to more ionizing events, while the positive ions are siphoned out through a grid at the end of the chamber. As they pass through this grid, high voltage accelerates them out the back of the spacecraft at speeds of up to 90 kilometers per second. For each ionized particle that the spacecraft can kick out, it gets a tiny kick in return. The whole system is powered by solar panels, so the spacecraft itself doesn't need to carry any kind of battery or power system, minimizing the total weight that it has to carry. The big problem is that the kick really is tiny. The thrust of ion engines is measured in millinewtons, like thousandths of a newton. Hold a piece of paper in your hand. That's the kind of forces involved. But they can operate for days, weeks, even months, accelerating and accelerating long after chemical rockets would have run out of fuel. So if you're already out of the gravity well of a planet, they're very efficient engines for dramatic changes in velocity. NASA and other space agencies have actually used ion engines very successfully in a range of missions. They've been developing this thruster concept for decades, but were never willing to risk it on an active mission where a failure could end it. So NASA gathered up a bunch of these risky technologies and packaged them together as the Deep Space One mission, which launched in 1998. Deep Space One was equipped with 12 different technologies that NASA wanted to test out, including low-power electronics, solar concentrator arrays, various scientific instruments, and a solar electric propulsion system. Its engine was run for enormous lengths of time, allowing it to make close observations of asteroids and comets, and even Mars. NASA doubled down on the technology of Deep Space One, giving its Dawn mission 3 redundant ion engines. These allowed the spacecraft to go into orbit around the asteroid Vesta, make observations, then break orbit and travel to asteroid Ceres and make even more observations. And it could still have fuel in the tank to visit even more asteroids. Just to give a sense of its acceleration, Dawn can go from 0 to 100 kilometers per hour in 4 days of continuous thrusting. Ion thrusters were used to carry ESA's Smart 1 spacecraft from Earth orbit to lunar orbit and on the Japanese Hayabusa spacecraft. Ion engines have been tested here on Earth and successfully operated for more than 5 years continuously. With these successes, we're going to see even more spacecraft equipped with ion thrusters in the future, but ion thrusters themselves are getting more powerful and resourceful. I said that ion engines produce very little thrust, but there are some ideas to boost their output. The first is dramatically increase the amount of electricity that you're using to accelerate the ions. Instead of solar panels, NASA considered creating an ion engine powered by a nuclear reactor. About 15 years ago, NASA considered a mission known as the Jupiter Icy Moons Orbiter mission, powered by the Nuclear Electric Xenon Ion System, or NEXUS engine. The spacecraft would be capable of exploring each of Jupiter's icy large moons in sequence: Ganymede, Callisto, and Europa. The spacecraft would have been launched into orbit in 3 separate pieces, which would then be assembled in Earth orbit and launched off to Jupiter. The spacecraft would use its 8 ion thrusters to study Callisto and then Ganymede for 3 months each, and then settle into a final orbit around Europa. If conditions were right, it could even go into orbit around Io. Of course, we don't get to have nice things, and the mission was canceled back in 2005. There are other ways ion thrusters can be scaled up. NASA is testing a high-thrust version of ion engines known as the X3 Hall thruster. This engine is capable of blasting out ions and produces 5.4 newtons of force. Again, not much, but remember that previous thrusters top out in the thousands of newtons. At the highest levels, this could be the technology that will carry human astronauts to Mars, cutting down the flight times to just a few months. Engineers are planning to run the X3 for 100-hour tests this year to see if it has the same kind of long-term operation as the smaller ion engines. The coolest idea I've heard recently for ion engines is the idea of an air-breathing engine under development by the European Space Agency. Instead of carrying any propellant at all, engineers at ESA demonstrated that a spacecraft in low Earth orbit should be able to pull in molecules of air right from the atmosphere and then ionize them and blast them back out. Since the spacecraft would be using unlimited solar electricity for power and pulling its propellant from the atmosphere, it could operate without refueling essentially forever. Spacecraft could operate at lower altitudes, and space stations could remain in low Earth orbit indefinitely without needing to be reboosted. It's going to be a real game changer. And not only Earth, this technology could be used on Mars or Venus or Titan, anywhere with an atmosphere. Ion engines have already made an impact on space exploration, and in the next few years, we're going to see more missions equipped with them. They could even be the engines that carry human astronauts from Earth to Mars in the coming decades. What do you think about ion engines? Let me know your thoughts in the comments.